Okay, ladies and gentlemen, I will proceed with the topic which we stopped in the morning. I hope it was not too boring, but it, in my opinion, is an essential point to understand. The problem what we always had in the European region is that we had geologists, and the geologists, we still have one, of course, they write books of things we never need. They tell us this geology comes from Paleozoicum, Precambrium. Nice to know, but for what reason? That's why we wrote a guideline which clearly specifies what the geologists have to do. And it says they have to work together at the end of their studies with the tunnel engineers. And what we do together with the geologists, and we need them, of course, is we make sketches which we understand. We don't need AutoCAD drawings, we don't need numerical simulations in an early stage. What we need is to understand how the geology is built up. And then we make quite simple sketches, which you see on the slide. We ask for a cross-section and we ask for a longitudinal section. And we call this the ground behavior. And we have 11 nowadays. This is an Austrian guideline, but there are several others. Now we say we have 11 classes, and dear geologists, please tell us in which of these 11 classes is the geology. And the typical picture is this one. This tells us as a tunnel engineer what happens if we do nothing. We call the ground behavior is a behavior what would happen if we build the tunnel at once in a full cross-section, what is easily possible in a hard rock, for example, but it gets a little bit difficult if we have, let's say, loose ground or bad rock conditions. And what happens in a full cross-section and without putting in any support. And you can do this now analytically, numerically, or you have the experience. However, we need to know what would happen to the structure if we do nothing. In this small example, the geologist gave us his sketch. Of course, he gives us the overburden, the expected water inflow, and those points, which I didn't put on the slide. And we have to understand what would be the result without any support, and then we come with the measures, what kind of support should be put in. And the same to a longitudinal section where we see, blocks will fall down, but it seems there's no high overstressing because there was already a geology existing which, let's say, was in favor with this blocky ground falling down. And we do that the geologist has to find out how many cross sections does he have to do along a tunnel. What are the typical, I would like to call it, homogeneous zones where we don't need every meter such a section, section what I did here. The problem is a little bit, as everything is automated and is computerized, that they would like to give us an information, let's say, every meter, or even every 10 centimeter. There's no need for us. It fills books and we get the brain full of information, but lose the real view, what are the problems in this tunnel. And then we go out and we need the geologist outside again, and we have to clarify if that what he did in the prognosis is really happening, because if there is a, let's say, major difference to that, we will get a claim of the construction company, and that's why we wrote a very special contract for underground engineering. Is not topic of this session today, not to get any claims anymore from geological, geotechnical points of view, and there is an easy way to do that. However, I just wanted to say the geologist has to make some pictures from the situation which is really outside then. But there's a main topic in between. The geologist must not be the same than did the prognosis, because our experience was that if the geologist who did the prognosis is the same, then does the, let's say, the pictures from what did we meet really, he always sees that what he did in the prognosis, even if it's completely different. And this got out a problem, and we have it now by law. there is no way the geologist who did the prognosis is not allowed to do the real geology outside then during the tunnel construction. A completely other, let's say, problem occurs when we have too high deformations, much higher deformations than we thought during the design. This is a picture of the Inntal tunnel where we had this 1 meter of radial deformation. As you see, the circumference line got much, much shorter, and that's why we had a completely destroyed support inside. What we didn't do at that time is we didn't make these slots. Of course, if you overstress a young shotcrete, you saw the shotcrete line in the last lecture already, we get not more than, let's say, 10 megapascal, 15 in a, let's say, 20 hours period, and the younger shotcrete will be destroyed if you have high deformations in an early stage. So to get rid of that, Rabčević had the idea, okay, make these slots, and we now did a little further development. If you have high deformations, we put in such a sliding element. This sliding element starts to deform before the shotcrete is destroyed. So we can tell the element by choosing the right material, I mean by choosing the right steel quality, the right length, the right number of the elements, at what force should it start to buckle. Because then if it buckles and the shotcrete has a little bit higher strength than this buckling element, then the shotcrete will not be destroyed. So we put in, as you see here, this idea of Rabčević, make slots in the shotcrete, but we said we would like to have an immediate force in the slot, so when it starts to deform, then these elements should be deformed. As you can see here, these steel elements start to deform and close the gap, but bring already support pressure to the shotcrete. So it's more than zero. In the Tauerntunnel, we had a load of zero there because there was nothing in, and the gap closed quite quickly. And we would like to reduce the velocity, and we do that by putting in such elements. There are other ideas. The Swiss, for example, developed the Hitchcon element, which is a kind of concrete, a poor concrete which starts to be deformed, breaks out, was not allowed in Austria because the working safety inspector said no blocks are falling on the miners, even if they are small, but this was not allowed. The Germans developed a very good idea. They, instead of putting the pipes in, they put in cylinders, you know, looks like a wine cellar. You put in lying cylinders, you could put in your wine bottle in until it is not deformed at least. And then you can bring a small resistance into this gap. And then it closes. And when it's closed, the shotcrete has its strength already and can take the strength if you did a good calculation for that. And you can make several slots, yeah, not just one. You make several ones for the Semmering base tunnel, which I will introduce you tomorrow. It's a 27 kilometer long tunnel tube, which we are right now under construction. We made a design for 1, 2, 3, 4 sliding elements, yielding elements, which will close when we are passing through the fault zone. Yeah? Of course, we have to make the excavation a little bit bigger so that it can come in for this distance, what we got out from the geotechnical design. Here you see a temporary invert, as we like to build a tunnel in several steps, a top heading and then a bench and then following with the invert. As long as we have this, it's a sketch for 2 designs, a flat temporary invert and a deeper ones, depending on the geological, geotechnical conditions. This one you would need if the situation is really a bad one. This one, if it's a little bit better one, there will be criteria who say, okay, now we choose this one. And you see, even in the temporary invert, we put in these yielding elements, not to destroy the shotcrete element, which is a passive element, as I described before. And of course, long boards to help the rock to get its cohesion back, to get a high cohesion or a higher, let's say, friction angle. Another point, what could happen, another risk, what could happen, but this happens more in shallow tunneling. So when we start at the portal location, we have not 1,000 meter, we start with, let's say, a shallow overburden, and then we have to fight against this so-called Terzaghi silo. So everything is quite old already from the knowledge. So this silo could come in, and you could make an easy calculation. Will this silo fall in the tunnel, yes or no, depending on the cohesion. This silo, of course, is depending on the size of your tunnel. And there you assume to have a circular shaped, like I did here, a circular shaped silo, and we had several silos already watched, and these silos are looking like in a school book. These are really almost circular, like what Terzaghi assumed at that time. You know the overburden, so you know the weight which is going down, and you know the forces which are working up here, because this is the cohesion times the surrounding area. So you can easily calculate if your cohesion is high enough to avoid a silo, yes or no. In reality, it looks a little bit different, because the silo does not go from here to here normally. It works almost always in the middle of the structure, and if your calculation set is absolutely no problem, you put up a little shotgrid shell, then you will see this risk, because you will see the cracks in the shotgrid shell. Yeah? You will see that this load is working on your shotgrid already. In connection with these problems, we always have the problem of a phase stability. So if we do not put enough phase stability in, I mean bolts in front, then this silo can happen. If you already stabilized your face area with, let's say, long boards, at least going through this, let's say, slope failure line, then you will avoid that this silo can come in. And you combine, normally we combine this one by putting in long four-poling elements, which we call nowadays pipe roof. There are several names used for that. So if we are passing a fault zone, we put in the long pipe roofs. These are pipes with a diameter of 140, a strength of the pipe of about 10 millimeter, and we fill it up depending on the quality of the fault zone. We fill it up, let's say, with concrete. We do holes in the pipes so that we can do grouting out of these pipes. These are methodologies. But this can be seen out of these ground behavior sketches with the geologist does in the first stage. Then we do our, let's say, simple calculations, and after that we come to the elements which we need for polling elements and face boards. So in a laboratory scale we can easily watch that, because if I have a small overburden here, I can show that this will walk in. Yeah? If we are going deeper, and the cohesion would be high enough to avoid this silo, and a silo does not occur, we often have the problem that we have this dome-like failure. So the rock tries, or the soil tries to get, let's say, its bearing capacity from the sidewalls, but if you have quite bad rock material inside here, you will have a collapse which does not go to the overburden anymore, because the overburden is too high, but then you get from the failure mode a kind of dome, looking like a dome, and that's why we call that a dome-like failure. And to see that a little bit better, I brought two films with me which I would like to show you to get it more realistic, some problems which were really observed. First, I show you a film where where it was possible to see the crack in the shotgrid shell. I do not start from the very beginning. As you will see, you will immediately see where the crack is and what then happens if you don't do nothing. You see the problem already?
Έσβησα ένα βίντεο στην αρχή και...
It's already far away now. Yeah? So the crack was seen much earlier.
Θα σβήσω τη φωνή εγώ τις μαλακίες που λέμε.
And it happens because a load is sitting on it. Why should it then...
Έτσι τράβηγα και πριν και μόλις έπαιζα δες πώς έκανα πίσω. Αλλά το τράβηξε. Το τράβηξε. Έλα μωρέ γαμημένο. Το κρατάει το χάρι. Γκρουπ κάνει μέσα. Είσαι! Ωπα το μάλλον καθίσει τώρα.
And the whole mass, which is in the dome-like area, will come down. So it's a little bit too late to react in this situation, of course, because you cannot repair that. We several times have colleagues on the caterpillar sitting and say, okay, I put my shovel on it and then it, please, get him out. This is a really dangerous situation if somebody would like to repair this in this situation. Another small example, face problems. No face support done, as you can see. And the whole mask comes in, and the face open. So these problems we can just avoid if we put in enough face support, and we knowing that the problems occur in the face area, latest 1 to 2 diameters back. I mean, I have a much worse situation on my photos which occurred in Austria some 5 to 10 years, no, 5 years ago. Compared to this last film, the problem was this material was quite dry, but the material in Austria was really wet. So this in this film it stops at the friction angle, then it stops automatically, but when it's wet it really flows out. I will show you a picture afterwards. So another problem what we can have is a ground failure. So if you get out your calculated forces out of this shell from any calculation, then you try to bring in your forces into this area here. If this does not work, first step is to make it a little bit wider. We gave the recommendation we shouldn't do it wider than 2 times the shotgrid shell, because we are already in a problematic zone. So if we do it, let's say a leg like this one, then we get the problem from this side. So if you have a problem in the area here, then we can use foot piles, or we can do a temporary invert, and this can be seen if it happens or not by careful monitoring. Again, this picture we had already. I wanted just to say we understood that we have this spatial arc, and what happens what we have to do is we have to make a ring closure which is not too far away. This normally helps. If the full ring closure is too far away, we can make a temporary invert. This helps a lot. you see that you have problems by tearing off the rock boards. If there is too little support in this area, the stress comes down here and will destroy your rock boards in this area, so your plates will spring off. And the other point, what we often see is that we have cracks in the shotcrete in this area because the arch would like to find enough force to be fixed on this side. This can only be done if we help the rock by bolting, intensive bolting in front, which we cut back then afterwards, and by putting in more shotcrete and more boards in this area. But this is the critical area. It is always 1 to a maximum of 2 diameters, which is concerned normally. What then happens, you saw already, we get these face support or face problems here, and on the other side the shotcrete is overstressed, and then we have a high risk of a collapse. What can we do? Let's say, if we didn't do it in an early stage, we can try to bring in boards to help this arch to be stabilized in an early stage. When we already have these shotcrete shells cracks, then it might be already too late. Gerard mentioned problems at the portal area. Yes, we several times see this, let's say, situation that the top heading or the tunnel is not fixed anymore with the shell in behind. We can see that outside if we see some movements here. And what I would say this is the biggest problem. When I was starting after the university at the German railways, we had several collapses like this one. And I had a checking inspector because I was working for a design consultant, and he said being underground and having problems underground is not comparable with problems at the slope area. Because to repair the slope area, because your entrance is then closed, you cannot do anything. You have maybe people in. How can you bring them out? So these slope problems are the most critical ones, and I would like to show you also 2 films of that. What happens if a slope problem occurs. I will take. I watched for some films in your. I hope in your language. It started to move on this side already. The question is, can this shotcrete ring now take the full load which is coming from the slope? We have a slope failure. You can calculate that by quite easy analytical calculations. For the moment it would look like could be repaired, maybe some stones are coming down, but then it goes quite quick then afterwards. And then the tunnel is closed. And if you have some people still in, to repair this situation is even more difficult because you have to have some machinery to climb up. Because we can't just repair it from above. Maybe another good example for that.
No, no voy capaz. Sí, no, corre. Venga, venga para acá, venga. Se cayó.
Shotcrete had already some cracks.
Santo Dios.
You see the crack here, opening. So what we learned out of these slope stability problems, and at almost every construction site we face some problems in at the longer railway routes. We have to spend much more money in these slope areas. This is what we learned, because this blocks us. The insurance companies, and normally we try to shift it to the insurance company and say geology conditions which have not been known very well. But the insurance companies getting more strict, more and more strict. So there must be a mistake done by anybody of us so that this happened. In Austria, we had also such a problem. Then we catched up an oil company with really huge borehole drillers, well-bore drillers, and they got out the people through these pipes. So portal problems have to be considered very carefully. Also here you can see already a crack in the shotcrete shell. We are not far away from the collapse. Some more examples. You see the shotcrete is completely overstressed. We have to be quite quick to repair that. This is the example which I wanted to show you from Austria, because nobody could imagine that this will happen. This is a dolomite. You see a main dolomite. It's really good compact rock quality, and we built the railway line with 3 tracks in there because the railway company wanted to have that one train can overrun the other. The slow trains are overrun by the fast trains. 3 tracks in there. And then we knew that we will face, let's say, a so-called ground moraine, which is a very bad material. But still, at this point, we had an overburden of about 100 meters. And nobody could, also not in the literature, could imagine that we will get a chimney failure, what I showed from the Terzaghi first, up to the surface when we have an overburden of 100 meters. But we had. And what we did is we knew that there will be water in. That's why we started the construction from around here with compressed air. So we built a wall. At that time, it was a construction company of Germany. They built a wall, a thick wall, so that we can start compressed air from this point on, which made the situation even more dramatic, because if something happens in the area where we use the compressed air, you cannot open the door immediately and the miners run out. Is not possible because of the compressed air, because then they are hurted because this delta of the pressure. So what I said before, we built this wall for the miners to go in, to brought on this compressed air level, and of course the material brought to this sluice, as we called it. But at the end, it happened that we had a collapse inside this area. And you have to know this is a full tunnel profile where the mud stopped at the right moment, so the miners survived which were in there. But if it could have happened that it fills up to the top point, and then surviving is not possible. You can choose, you open the door and you lose the compressed air from one moment to the other. But in good luck, it stopped. But you see, it didn't stop by lying under the friction angle, which we had in the last film, which we saw at the phase problem. We had a big problem because the material flows, yeah, because so much water in. Conclusions. Description of ground behavior should be done very carefully by the geologist in a way that the engineer can really deal with it. Stop writing books. This is our recommendation. Just do that, what the next engineer needs. This is just an overview of these typical ground behavior types. I didn't put on all the 11, but you have it in your books. Then reasons that can cause a cave-in exemplarily. Of course, there might be geology, non-predicted fault zones. This fault zone, what I showed you, was a non-predicted fault zone. This is often a reason why we have this cave-in. Unfavorable lithology sequences, unfavorable position of the joint sets, groundwater, and of course also overburden. Then there might be, let's say, some small mistakes in the design. The excavation method is maybe the wrong one. The support elements were not chosen in the right one, and the driving velocity. You can imagine, now we know what is the velocity of the hardening of the shotcrete. We know exactly at what time does the shotcrete have which strength. And then if we drive faster, and this 1 to 2 diameter effect of the stress redistribution works, it could happen that the stress goes on the shotcrete shell, but the shell cannot take this high load. That's why we put on the design drawings a limitation of, dear construction company, you are allowed to drive with this velocity, using the materials which we had in the tender. We never tender materials of the highest quality, so that we give the construction company a room for using better materials, because they would like to drive faster. But the cost for these better materials is then, of course, on the bill of the construction company. It's their duty, because they would like to drive faster. But it's a really important thing, driving velocity, to give a limit, what is the allowed velocity, so that all the support elements can get their full strength. The construction material, of course, and the insufficient exploration. Then we have the numerical calculation. There I come back when I speak of monitoring, of course, material model. I mentioned shotcrete is often modeled by linear elasticity, nothing to do with the reality. And this goes further to the material model of the soil, of the ground, of the rock, and so on. So that must be clear, even if we do these colored pictures, far away from the reality. This must be clear. It gives us let's say, an idea what can happen, but it's not we do numerics and then we have the exact results. This is not the case. Then construction itself, qualification of the staff is not always the best. The problem is we deal with a high fluctuation in our field. Then the used support elements and drive interruptions. If we have a drive interruption, for example, we have a Christmas break, then all the stress gathers at the face. We have to be very careful when we start again with the construction, because all the stress is sitting on the face. That's why we monitor the face during Christmas break and see what stress is on the face, and we carefully start again, and then it goes up full speed. But these interruption drives are not good ones. That's why normally we work 24 hours, 7 days. I think this is also done in Argentina. Organization, communication can be a big problem. Interaction of the involved parties, I will show you an organigram, and the correspondence afterwards. This may lead to some problems, and the question always is, would this cave-in have been avoidable? Then the funny thing is, the one party takes an expert, the other party takes an expert, no one of them were on the site, and he goes to judge, and the colleague who makes the decision, who has no idea of tunneling because he is a lawyer, makes the decision. And that's why we say we would like to get rid of everybody. We have to solve our problems ourselves. Because I'm sometimes invited to be an expert, but I always say to colleagues, I was not on the construction site. You must know how you did it in detail. And if you listen at when you sit here besides the lawyer and you listen what happened, you think the colleagues were on different construction sites, really. Most cave-ins were caused mostly non-predicted fault zones, water inrush, washing of joint fillings, coming across non-predicted sand lenses, water lenses, often cave-in in the area of the face, what we saw on the film already, and unexpected loads on the shotcrete shell. Because of that, we say we have to do monitoring. I'm almost in time. because I switch now to my next lecture, which is called Monitoring. Why is it necessary to do monitoring? But I think I showed you some examples already where monitoring could help to get more clever.